Here's the schedule for the rest of the day today. We're a little bit behind, so I might throw this one now after lunch, depending on how quickly I can go through the parallel one. So let's say again, we're going to have this OpenSees challenge at 2:13. I'm hoping to get this in before 5 to 5, so everybody can get their bus that needs to. So this talk basically is about parallel processing with OpenSees. Go back to the day when I started OpenSees. It was actually started so that I could do my research in this area, which is why I always do a talk in this area. Because pretty much I believe that by the time you guys are done, you graduate students, you're going to be using this. You're going to be using parallel processing. You're going to be using the cloud to do your analysis. You're not going to be using your desktops anymore. So quickly, as we saw yesterday, the whole simulation software, it's sitting on hardware, and that hardware is changing. Bell's law, basically every 10 years or so, they keep making advances in computer hardware and stuff so that we're changing our platforms in which we do our work. Currently, back in 2003, we basically hit a wall with how much faster the processors are going. Those of you who are old enough and remember, before 2003, you go out and buy a new computer every 2 years and it'd be twice as fast as the one you had before. In 2003, that stopped happening. So the computer manufacturers they're still increasing the number of transistors they're getting on their chips. Moore's law, every 2 years, to double the number of transistors, but they couldn't make them go any faster. So what they started to do is just throw more processors onto the chips. So here are Intel's fastest computers about a year ago. These are their gigaflop performance. But this is what my child plays with. My 8-year-old daughter plays on machines that are, almost 5 times faster than my expensive desktop computer, and cost, a third of the price. So back in 2011, the late Steve Jobs gave a famous keynote address in which he declared the death of the PC, or not the death of it, but the demotion of the PC. It's no longer it's been relegated now to just another device like your iPhone or your tablet device. That's pretty much all it's useful for. Looking at stuff online or doing stuff elsewhere. Because basically all the work is going to be done in the cloud. Some of the people think the cloud is just a big hard drive in the sky, somewhere to store your photos and movies and your documents. It's actually not that. The cloud is also a place where you can do your computation. There's resources available for computation. The cloud computing resources that we have available to us. In those in industry, they have commercial cloud services available. Most of us are in research. For us, we have what are called these dedicated high-performance computers. We've also got the grid. So basically, what is a parallel computer? Basically, we've got a whole bunch of CPUs. They can talk together. There's some memory somewhere, and there's a file system. And depending on how close these components are, just kind of distinguishes it between a high-performance computer and a sort of a distributed computer. So where are we going? The fastest computer right now is a little under 100 petaflops per second, which is, you see, this is my laptop down here at 12 gigaflops, so it's like almost 1 to the 7 more processing power available to me than is available on my desktop. By 2019, we're supposed to be hitting the exaflop thing. However, the thing about these really high-performance computers is they get their high performance just by the number of cores or processing units that they have. Right now, the fastest one is a little over 500,000 processors. By the time we get to the exaflop, they're expecting between 10 and 100 million processing units available. So why do we care? Because they'll save you time. They allow you to solve much larger problems. Regional problems can actually be solved on these high-performance computers or these parallel computers. And whether or not you like it, they're here. I've got 4 cores on my little laptop here. With NISA, we've available, machines with over 100,000 cores or processing units available to us that you can use right now. If you go to NISA and submit a job to one of these parallel machines. But before we get all excited about all these hundreds of thousands and millions of cores, there's something called Speedup. What we'd like is when we go to 1,000,000 cores, our program is going to run 1,000,000 times faster. That's called a linear speedup. So linear speedup typically doesn't happen. Amdahl's law is a famous thing in computer science, where he breaks down he looks at he recomputes what the speedup is, basically breaking it down into that portion that must run sequentially, and that portion which can run perfectly in parallel. So this alpha factor turns out to be very important. If alpha, for example, if 10% of the program has to run sequentially, the maximum speedup we're going to get, no matter how many processors we have, is 10. If 50% of the program has to run sequentially, the maximum speedup we're going to get is 2. So even though we've got these millions of cores, we're looking at a speedup of 2 or maybe 10. If that's how much of our job just has to run sequentially. So basically, what they've found, or they've noticed, is it's not, when we go to these parallel computers, as I'll show you in a minute, we're struggling to get speed up. It's not just us. Basically, across all the usage of these parallel computers, they've noticed that, even though they're giving you these much more powerful computers, nobody's really gaining any performance improvements. We're kind of flatlining. Nobody really knows how to make use of 100,000 or 1,000,000 cores. So it's a challenge to all the communities out there. It's a challenge that we have. What can we do to make use of all these cores? So OpenSees, as I mentioned yesterday, this is what it is. It's a software framework for building applications in structural and geotechnical engineering. And these applications are both sequential and parallel. The classes, there is stuff built into the code that's always been there for the parallel and distributed processing. I release 2 interpreters for parallel processing. I briefly mentioned them yesterday. In the next few slides, I'm basically going to go through them and show you what they are and what they do. But these 2 interpreters are SP and MP. So SP is an application for large models. If you have a model with 100,000, 300,000 degrees of freedom, you might want to consider looking at SP. The other application is basically for doing parameter studies, Monte Carlo kind of simulations. It also does large models, but I'll show you what you have to do to actually build a large model yourself. But sometimes if your model gets so large, this one might not work with SP. Or if there's commands in the model that SP just can't handle, you just have to go to MP anyway. So what is SP? So we all know what when a regular interpreter is running, is just one interpreter running on one process. And that's the same thing with SP. We have one interpreter running in one process, and that's the process that's processing your input file. All the other processors are just sitting there waiting for something to do. As you build the model with SP, everything is getting added to that one processor. So all your nodes and elements, when you create your analysis, all those objects are actually added to that P0 process. So this is the state of the situation after we've sort of created the analysis static, as we've gone through that many steps in the script. It's only after we've we issue the analyze command that we actually internally do some domain decomposition, where we'll take our model, we'll split it up into different parts. Different elements and nodes are going to go spread out to the different processors. The element state determination is going to be done on those different processors. So if we go back to Moore's law, like all this is totally parallelizable. There's no communication here at all. So this whole thing works perfectly in parallel. Our problem is solving AX equals B. Initially, this can all run in parallel. As we start doing our Gaussian elimination, there's a numerical analysis. You'll learn something called the Gaussian elimination tree. So as that tree starts narrowing towards the top, there's just so much communication has to go on, and eventually you get to a point where everything is just done sequentially on one processor. And that's the part that is going to kill us later. Basically here's where we start to die. Typically on 2 processors we'll get a speedup of almost 2. As we start going more, we start flatlining. In this example we get a speedup of about 6. After that, throwing more processors at it is not going to help us. Now this one is using a implicit integration and a direct solver. Alternative solution, this is a totally made up problem. We're going up to 75 million degrees of freedom. It scales almost perfectly. So what he's done is he's gone from implicit to an explicit integration scheme. And doing that allows basically a linear solution algorithm. And also he went with a direct diagonal solver because all you solve the matrix equation is just a diagonal matrix. And that scales perfectly. You just form the components on the different processors, and there's no communication required. They can all do the work independently. So as engineers, as we go to these machines, we might have to think of redoing what algorithms we're using. Instead of using implicit with direct solvers, we go to explicit with diagonal solvers or maybe even conjugate gradient. So the other interpreter, NP, basically large models and parameter studies. So the difference about NP and SP is on NP, every single process is running an interpreter. Okay? So your script that you start goes to every single process. And based on what's called and each script can actually determine what its unique process ID is. Each processor will, in the computation, will have a unique process ID going from 0 to n-1, where n is the number of processes running. And they'll also be able to figure out how many processes are in the computation. And based on their process ID and their NP, the number of processes, they're going to do different computations. They'll build the model in different parts, or they'll do different parameter studies. So with NP, what we had to do, we put in some additional commands. If anybody's done any parallel programming using MPI, they'll recognize these commands. These commands are in any parallel programming language. Basically get NP and get PID, get the number of processes, and get that unique process ID. You can also send and receive messages between processes. There's a command called barrier. Barrier is important in that every single script must have that barrier, and when all the processors will actually stop until every single other process has actually reached that same point in the script. So if there's a barrier, you know that all the processes are going to hit there and wait until they go on. That's important because parallel programming introduces other problems. It can be a lot more difficult. I'll talk about those problems in a little bit. So this is just one simple script. I believe you have it in the downloads. All I'm just basically showing here is getting process ID, getting NP, sending and receiving messages, and this barrier command. Basically every process other than 0 is going to send a hello world message to 0. 0 is going to receive these messages and print them out onto the screen. So this is how the students are making their scripts run in parallel. They're using the fact that they can get NP, get PID, and do different computations based on those two pieces of information. And all they really have to do is take their original script in which they have their for or the for eaches, and add 6 lines of code. Now you can add this 6 lines of code to your sequential script. It's not going to break it. It's still going to work. But these 6 lines of code, then you'll get that process ID, get NP. I set some variable count equal to 0. And then inside your for each statement, you basically switch. Each processor does one unique analysis based on the count, this variable count, modulo NP. That's going to return an integer number 0 through n minus 1. And if that is equals to the process ID for that processor, it actually does the computation. Otherwise, it doesn't do it, jumps out. And then down at the bottom, you just have to increment count by 1. If you don't increment count by 1, only one job will get done. So here's an example. So we did 10 days worth of work in 15 minutes once we got it running on a machine. Here's another example. 113 records, and then four things for each record. So again, we have the 2 for each loops. And what we did is inside that inner loop, we put that that same line about count modulo NP equals process ID. Again, we have this increment count. And we were able to do 2 months worth of work in less than 5 hours on one of these machines. My final example, there's basically be 4 for eaches. Again, we put that if in that inner for each. Basically 2 years' work was done in 7 days on one of these machines. And they could have done it a lot sooner. The only thing is they only went for like 200 processors. They didn't go for as many processors as they could have used. I'm not sure why they did that, but they did. So the interpreter also has some additional commands for when we want to do these parallel models, when we want to do the domain decomposition and do a large model using SP or NP. So these commands, we've added some additional numbers, parallel plane and parallel RCM. We've got a parallel solver, mumps. And then if you're using displacement control, you have to specify parallel displacement control. And the important thing, you only use these if you've got a parallel model. If you want to do these sequential, these independent things, do not use a parallel number, do not use a parallel equation solver, because then what it will try to do is, it'll try to make one big model out of all the models that are going on. So it's going to crash and burn, because it can all be going through different steps in the analysis. So these are only for the case where we have a large model we want to analyze in parallel. So here's the simplest example I could come up with, the one we went through yesterday. Basically, I'm going to run this on 2 processors. I'm going to put element 1 on processor 0, and elements 2 and 3 on processor 1. Because I'm putting this element in processor 0, I have to put nodes 1 and 4 on processor 0. So here I am, I'm getting the process ID, getting NP. If NP is greater than 2, I just exit, because this script will only work for the case where we have 2 processes. So if my process ID is 0, I'm going to add nodes 1 and 4. I'm going to fix 1, I'm going to add this element to it. And I'm also going to add the load pattern, in which I have the load at node 4. In the other processor, I'm going to put these 2 elements. So I've got the 3 nodes, nodes 2, 3, and 4. I have to fix nodes 2 and 3. And then I have to add the 2 elements. The important thing to note in this simple model is that you do not put 2 load patterns with load 4 at both of them. If I did that, I would be doubling the load in my model. So for nodes that are common between 2 processes, you don't duplicate the loads, nor do you duplicate the masses. This was a transient problem, because you don't want to be doubling up on anything, okay? So as I say, it's a simple example, but it makes the point. So here's the parallel analysis. So pretty much all the commands you've seen before except the ones in red. As I said, you had to use a parallel number when you use the parallel MP for parallel models. So I'm using parallel number and I'm using a parallel solver to test the mumps. So basically, here's the results when I run it. It's good to see that node 4, because they're printing, both the process interpreters are printing the results at node 4. You see you get 2 node 4s coming out to the screen. And the nice thing about it is you can check that, hey, yes, the nodal displacement at node 4 in both these processes is actually the same. So both nodes do have the same displacements, quantities, and velocity. So now here's the other one we have to worry about is the displacement control. As I say, the integrator is no longer displacement control. You have to specify parallel displacement control. And this is just because if the node you want to control is only in one processor and it's nowhere else, the other processors have to know to, well, how do I go get that? How do I go get it? And one thing about whatever type of analysis you're doing is this domain change. Anytime you change anything in the model, like you add a new load to one of the processes, you remove elements from one of the processes, you have to issue this domain change command. That's basically, we have to go renumber the equations and stuff when you add new things, new nodes, new elements. So this domain change just tells all the interpreters that something has changed. Next time we go into an analyze, we have to redo the mapping between the nodal degrees of freedom and the equations. As I mentioned, parallel programming, it can introduce more problems into your model, serious problems. The things to watch out for are deadlock. Basically, the program hangs and it doesn't seem to be going anywhere. Why is it not going anywhere? Typically, it's the send self and receive self is a little bit messed up. You can have two processes sending information between each other, and if you don't do the send and receive right, one of them can send the message and then wait there, waiting to receive the message, while the other guy is still trying to send the message. So they just, the send and receive just isn't done correctly. They have to match perfectly. If this guy sends, this guy receives when he's sending. If that's not the case, this program, you're going to get deadlock. Other thing that can happen if they're sharing the same file system, one process opens up a file and writes data into the file. The other process won't be able to write to that file until that file is closed. So if you don't close the file to the end of the program, then you might have a send and receive that are perfectly matched inside it later. It's not going to be able to get past that. So it's just going to hang there waiting for that file to become available. So again, you'll get deadlock. The real nasty one, deadlock is easy to find. The nastier ones to find are what are called race conditions. Every time you run the program, you get a different answer. It's called the race condition. It can be due to the file system, but there's lots of other stuff that can go on. As I say, these things are really difficult to track down. You have to go back to your script and back to your program and try and figure out, what sequence of events is leading to these two things coming up with different answers. Now you'll find you can get race conditions or different answers depending on the operating system on which you're running, depending on Windows or Linux. You can actually get different answers when you run OpenSees. It happens it's not just OpenSees, it'll happen with other codes too. The compilers spit out different object code. The instructions they're giving to the processor, even though the processors might be the same, the instructions they're getting are different. They can be adding numbers in different orders. When you start adding large numbers and small numbers, you can get round up and things start getting dropped. So that can affect the answers. Another thing to work out, especially for parallel, is load imbalance. Basically, one processor is getting all the worst analysis jobs. All the other processors are staying elastic, and this one poor sucker is just getting everything that goes nonlinear is happening with him. So he can be dying. trying to get through all this analysis. All these other guys will be flying by and they'll be done, say 10 times faster than the guy who's gone nonlinear. So if that happens, the scripts I was showing do not take account for that. There are other things you can do, but they're just more complicated than 6 lines of tickle script. If you have that situation where you're doing these tens and hundreds of thousands of analysis and you suspect that load imbalance is going on, just send me an email and I'll show you how to do it. This is just a little bit more complicated. So if you have a parallel job and you want to submit it to NISA, I would say right now you have access to these machines with 100,000 cores, crack them in steel. You basically select the machine, select whether you want to use SP or you want to use NP, and then you specify the path to basically where the example is. And what you want to do is because how NISA works, well, they take your files and they'll send it to the parallel machine. All the files that your script needs has to be in the directory where your main script is, either in that directory or in directories below it. If it's in a parallel directory or one directory higher, when it gets to the parallel machine and starts running, it's not going to find the files. For example, people typically put their ground motions, say, in their home directory, and their scripts will just reference the ground motions in their home directory. Well, that won't work with this. What you have to do is make sure that ground motion directory is inside the folder in which you have your main script. Oh, and one other thing I should mention. This wall time, the default one that I've set up when you start this is for those small examples. They're like less than a minute. It takes them to run, so I've set them up for a minute. It makes them run faster. It makes them, they get it. Once these jobs go to the parallel machines, they go in a queue. That queue can be quite long and lengthy to get through. Sometimes they let smaller jobs just head to the top of the queue. They get up there. If there's a machine running and it's got some available nodes, they'll just send these quick jobs through. So that's how I'm able to get them through. But the problem is if people just stick with the default, when they run their big job, it's not going to finish. And these machines actually kill jobs when they start exceeding the wall time. So you have to, if you've got a big model, you have to up that wall time. The maximum that they allowed on the 2 machines that we have right now are 24 hours. So that's the maximum that you can set it. There are other machines that they have available at Purdue, Carter and Hanson, that I believe allow you to run a job for 72 hours. But they have nowhere near 100,000 cores. The number of cores they have is limited. So that's high performance computing. Now I'm going to talk about sort of the grid computing, the other end. Basically, it's the most distributed form of computing. The problem is the communication is very slow. These computers are communicating across the network. They're competing with people downloading movies and watching YouTube stuff. So there's all this. That's the stuff. That's the speed of the communication between the machines. It's typically only for the very embarrassingly parallel jobs. Our parameter studies fit perfectly into this computing model. So here's the Open Science Grid, which is what we have available through NISA, which basically little computer centers with clusters of machines. Just they make these clusters available to researchers when they're sitting idle. Now, as engineers, we often need to integrate diverse components, automate our processing steps. Like we're doing the same thing over and over again, say with just different input files. We're just repeating the stuff in the different inputs, trying to reproduce results. We're sharing our data. There's a whole bunch of stuff that we do that's not unique to us. Lots of researchers do it. So software does exist to actually help us do all this stuff. It's called scientific workflows. And basically, this software allows us to run our workflows, but importantly, it allows us to run this stuff on the cloud. It allows us to run it on the open science grid. It allows us to run it on these high-performance computers. The software they have available on NISA is called Pegasus, which is coming from USC. Basically, this is their slide. It's a planner trying to figure. It figures out what the workflow is. You know, which jobs can actually be run in parallel, and which jobs run sequentially. You know, which job has to come before some other job. Which of those jobs can run in parallel, and it moves the input files and the output files around between the machines, and it starts this stuff up for us. They have told me that that Pegasus can handle up to a million different jobs at any one workflow. So it's, you know, it's what they can do is it's impressive. Now, to build one of these jobs, you provide what's called a DAX. You have to describe what that workflow is. It's an XML format document. Based on this description, they take it and then figure out just exactly what needs to be done. Like to you, it's just, well, I want to run this application with this input file, and this output file goes to this other machine. These guys go figure out, well, to run this input file with that application, first of all, I have to, you know, send that data across to some other machine. I have to go find the machine that I'm going to run it on. Then I take it over, I run the job, I send the files back, and then I have to clean up the data on that other machine. So there's a lot of stuff that they figure out that they have to do. So our simple two things to do job came out to be, you know, they have 9 things to do to actually do this 2 jobs. And these are the 9 things we'd have to do too. And we would have to send our files across, run the application, take the files back, and then clean up the machine on the other side. So here's the simplest example I came up with, just to test this whole thing. Basically, I'm using MATLAB to generate Monte Carlo kind of simulations. I'm using MATLAB to generate all my material parameters based on some distribution that you specify. I'm running OpenSees. OpenSees is running, all these jobs are running in parallel, embarrassingly parallel. They're each doing a separate simulation with the material properties. The results are basically coming back to MATLAB, and MATLAB is then just plotting the results. I've actually run up to 80,000 parallel OpenSees jobs at one time. It pretty much was maxing out, not the Pegasus system, but the system on which NISA was employed, because it was just running out of memory to figure out where everything needed to go. So this was if you look at the OpenSees lab tool, this moment frame reliability analysis is that tool. You basically specify how many little Monte Carlo simulations you want to run, and it'll run through all the simulations. For each ground motion, it basically, this is a little steel frame building. Each element gets different material properties based on the steel you specify and the sort of meaning that the distribution for F, Y, and E. Any questions? Question?
Is there any criteria to select the solvers?
Basically, if you're going parallel, the only solver you want to use is MUMPS.
Is it available on our system?
It's available on these systems, yes.
No, like laptops and desktop.
MUMPS is available in the parallel version that you have.
Okay.
I'm trying to build it sequentially. I have built it sequentially. My problem is it's failing for certain large matrices, which it should. Now, when you have it sequentially, and if you can actually run it, even though you get the parallel version, you basically install MPI, and if you run it with n equal to 1, so if sometimes as people have problems with large models, but if you just run it with one processor, so you run a parallel job, you specify only when you use one processor, and you use MUMPS, you will find that it will go a lot faster. The best example I have is this guy right here. I'm showing the results for MUMPS. It was 6 hours to run a MUMPS. With the other smaller solvers I had, it was taking days to run. So we were able to go from days to hours just by changing the solver to mumps, which is why I'm trying to get mumps in the sequential one. Pedro is dying to get it, but as I say, I'm just having a problem. Internally, it's failing in a number of large systems. Just trying to track down why it's failing when it runs with NP equals to 1, so it should run sequentially. So if I can find out the problem, it'll be in the next release. And then I will not even mention the other solvers when I do my talk, because it is just so much better than all the other solvers we have. Another question?
When we compose our model for the OpenSees NP, is it better to divide them like equally, like the model, the nodes between the...
If you know it's going to be say you got a big tall shear wall and you expect all the problems down at the bottom, you don't divide it equally. You put, the guys at the bottom, so you don't get load imbalance, they have a much smaller number of elements than the guys at the top. It'll make a big, that was the focus of my research. Basically I was doing, you have an initial partition, then you get all this load imbalance, what do? So I'd start moving elements and nodes, and I was coming up with algorithms, which elements and nodes do we actually move to which processors. That's why OpenSees was started up. But that feature is actually not available in OpenSees, because it breaks the recorders. I didn't think about recorders when I was doing the whole thing.
So is the problem with recorders solved, like with the parallel version, we have to use the...
Well, the recorders work fine with parallel. The only problem is when I was doing the load balancing and I was moving elements and nodes around, the recorders, when they're initially set up, they got all their pointers to the nodes and the elements. When I got nodes and elements moving around, the recorders were segmented. I could clean it up, but it's then trying to figure out the order of putting all the data back together so you get the same output file as you get from the sequential one. It would just take time to do. And I'm not paid to do any code development anymore. I get my wrist slapped. Sorry, Pedro. Pedro here.
You broke my
I broke his thing. I get my wrist slapped by NSF.
You will get your head.
Don't worry.
I'll buy you a new one.
No problem.
So any other questions?